Dear student, this is our class or lecture number 4 on the chapter partial differential equation, and I hope that you have already studied the previous lectures. And in this lecture, we will focus on the heat conduction equation, solution of uh, heat conduction equation. Okay. Heat conduction equation first, its form, and then solution of heat conduction equation. Okay, for in cases of one-dimensional Cartesian coordinate, then two-dimensional Cartesian coordinate, and after that two-dimensional polar coordinates, and after that at the end of this or the final topic of this lecture or class will be some problems on different partial differential equation. But in this, before starting this or begin this lecture, I will suggest you that I have carried out the solution of heat conduction equation in one-dimensional and two-dimensional Cartesian coordinates, and then the two-dimensional polar coordinates, and the rest coordinates are three-dimensional Cartesian coordinates and three-dimensional cylindrical coordinates and three-dimensional spherical coordinates. And you can follow the same methodology or process that we used in case of wave solution of wave equation in three-dimensional Cartesian, cylindrical, or spherical polar coordinates. So just go to or just go to or view or look the previous lecture, just previous lecture, and then you will understand the process by which you can solve conduction equation in three-dimensional cases, that is in three-dimensional Cartesian polar or spherical polar or cylindrical coordinates. And you have to practice this. I am not I have not solved the heat conduction equation in three-dimensional cases because already we have known how to solve this, and the heat conduction equation can, in case of heat conduction equation, you can follow that we used in case of wave equation. So in this case, we will limit our solution of heat conduction equation for one and two-dimensional Cartesian coordinates and then two-dimensional polar coordinates. Let us begin our lecture. First, conduction equation. We know that the familiar conduction equation, heat conduction equation, that was we have already known. The form is del u del t, that is equal to h square del t u del 2u del x square plus del t u del y square plus del 2u del z square. That is equal to h into cat square u, where cat square is nothing but the Laplacian operator, that is del 2u del 2 del x square plus del 2 del y square plus del 2 del z square. And here you remember that you use the temperature function, you use the function of temperature, that is use the temperature function, and t is the time, and h is the diffusivity. In the steady state, you should remember that in the steady state there will be no temperature gradient, that is del theta by del t, that is there will be no flow of heat, that means del u by del t, that will be 0. And in that case, this equation reduces to h square, and this term, that is equal to h square, will be here h square cat square u, that is equal to 0. And in that case, heat conduction equation will reduces to Laplace's equation. Will reduce to Laplace's equation. Now come to the point how to solve the process of solution of heat equation, or better, it is better to say heat conduction equation. First of all, we wish or we want to solve it in one-dimensional Cartesian coordinate. And here I am writing the heat conduction equation in one-dimensional cases. In one-dimensional case, these two terms will be absent there. So one-dimensional heat conduction equation can be rewritten from this equation, that is from equation 1, as del u del t is equal to h square del t u del x square. Now to solve this equation, we can employ the method of method of separation of variable. Okay, and in this case, we know that the function u can be written as the product of the function of x and t, that is uxt is equal to x function of x and t function of t. And from here you can easily understand that the value of del u del t is equal to x del t dt by d capital T by dt. And similarly del u del x is equal to t del a dx dx, and then del u del x square is equal to t d2x dx square. And now substitute this value of uh, del u del t and del 2u del x square in equation number 2, because we done it, we did it several times, in solving different equations in our previous classes. So so in this case, if we don't go in full or complete calculations, there will be no problem. I think there will be no problem, because you are very familiar to solve this type of equation, this type of partial equations, differential equations, using the method of separation of variables. So here now, just from you can find it, or you can write, or you can obtain from equation number 2 that x d dt is equal to h square d2x dx square. Just now dividing both sides by x and t, you can obtain 1 by t dt by dt is equal to h square by x d2x by dx square. And you know that the left hand side is you can understand that the left hand side is the function of only t, and the right hand side is the function of only x. So you can say that this term is constant with respect to x, and this term is constant with respect to t. So you can easily say from here that both of these terms are constant, and that say that the constant is minus k square. And in the where k is the separation constant, k is called the separation constant. So now you can obtain two ordinary differential equation from this partial differential equation. One is for this equation, from this equation, one is 1 by t dt by dt, that is equal to minus k square, and another is h square by x d2x by dx square, that is equal to minus k square. Now we have to solve these two equations. Now come to the first equation. From here you can write dt by t is equal to minus k square dt, or from here if you integrate both sides, you can obtain that ln t is equal to, it is log t logarithm natural logarithm t, that is equal to minus k square t plus say l log a1. a1 is log a1 is a constant. So from here you can write log t is equal to minus log of t by a1, from this and this, log of t by a1, that is equal to minus k square t, or t is equal to a to the minus k square t. And come to this equation. From here you can write this d2x by dx square plus k square by h square into x is equal to 0, or d2x by dx square plus alpha square. Alpha square is nothing but k square by h square, or alpha is equal to k by h, that is equal to 0, and this gives you a solution. X is equal to a2 cos alpha x plus a3 sin alpha x. Obviously these a1, a2, a3 all are arbitrary constants, and you know the process or method how to solve this equation, but you can say, or you can understand that the solution of this equation will be this. So now the general solution will be that is xt equal to x function of x and t function of t, the product of these, and just substitute the value of t and x from this relation and this relation to here. So finally we get uxt is equal to a1 cos alpha x plus b1 sin alpha x e to the power minus k square t. Obviously remember that in this case a1 is equal to a1a2 and b1 is equal to aa3, sorry, aa2 aa3. So this is the complete solution of the heat conduction equation in one-dimensional case. Now you can impose, or you can apply the following boundary condition to find out the arbitrary constants a1 and b1. And here are some boundary conditions. So the number one is u is equal to 0 at u is equal to 0 when x is equal to 0 for all of t. That means u0t is equal to 0, and then u0 when x is equal to l for all t. That means ult is equal to 0. And number 3 is u is equal to fx, function of x, at t is equal to 0. That means ux0 is equal to fx. So these are the boundary conditions, and we have to apply these boundary conditions to find out the values of the arbitrary constants a, 1 and b1. Now applying the boundary condition number 1, that is this one, that means u0t is equal to 0, and applying this in this expression you can find out that u0t that is equal to, from here, a1 x is 0, so this will give you a1 into cos 0, that means a1 into 1, and this will give you b1 into sin 0 means 0, that is b1 into 0, and then this term is here, no problem is there. So we can write from here that a1 plus b1 into 0 to the minus k square t is equal to 0, because you know that u0t, you have given u0t is equal to 0. So from here you can easily write a1 is equal to 0. Therefore from this equation, the general solution, this equation will reduce to uxt is equal to, since a1 is 0, so this term will be absented now. So b1 sin alpha x it will be minus k square t. Nothing is different from of that. Instead, this term is not here because a1 is equal to 0. So now from the second boundary condition, that is boundary condition number 2, when x is equal to L, u is equal to 0. Now writing x is equal to L in this expression, we have so ULT that is equal to 0 from the condition number 2, and that is equal to, from here b1 is here sin alpha L e to the 1 k square t, and since it is equal to 0, you can write this term, that means sin alpha L, that will be 0. You can write from here sin alpha L is equal to 0, or sin alpha L is equal to sin n pi, where n is 0, 1, 2, 3, etc. From here you can find out alpha is equal to n pi by L. So now the solution for u becomes uxt from this relation, obviously b1 sin n pi x by L, that is here I substitute here the value of alpha. So b1 sin n pi x by L e to the minus k square t. This is equation number 4. Now if you take all values of n, then there will be different constants like b1, b2, b3, etc. So you can integrally write uxt is equal to n is equal to 0 to infinity. In this bn sin n pi L n pi x by L e to the minus k square t. This is equation number 4. And now we wish to apply the boundary condition number 3, that was u is equal to fx at t is equal to 0, that is ux 0 is equal to ft. Now write t is equal to 0 in this expression. You can obtain from here u that was given fx, that is equal to n 0 to infinity bn sin n pi x by L, that is here, and e to the power 0 means 1. Okay, no problem is here. So now multiply these fx with sin n pi x by L and integrate it from 0 to L. Then what we will get, that is equal to 0 to L fx sin n pi x by L dx. That will give you, that is equal to, from this expression, that is equal to half. I have multiplied by half, so I have to I have written here 1 by 2, so 2 should be multiplied here. So okay, no problem, 1 by 2, so into 2. So this is no problem. Now integration 0 to L, write the value of bn, write the constant here bn, then this 2 appears into it is half, and then sin n pi x by L was there, and another sin n pi x by L, so sin square n pi x by L dx. That is equal to bn by 2, and you can write 2 sin square n pi x by L as 1 minus cos 2 n pi x by L dx. So if you integrate, this term will give you sine term, and so if the limits 0 and L are used, then you will find that this term will give you 0 null result. So only the value that will give this expression is for this dx, 1 into dx. So then go to that bn, here is bn by 2, that is here, and here this will give you 0 to L integration 0 to L dx, and dx will give you x, and if you use the limit 0 to L, that will give you L, that is equal to 0 to L, and this term fx sin n by x by L dx. And from here bn is calculated as 2 by L 0 to L fx sin n by x by L dx. So therefore the complete solution is given here uxt, that is equal to, from you can see this expression, this file. So So n is equal to 0 to infinity, the value of now dn 2 by l 0 to l fx sin n by x by l dx into this sin n by x by l, this sin n by x by l, that is here, and after that the final last term is e to the minus k square by t. So this is the complete solution of heat conduction equation in one-dimensional Cartesian coordinate system. Now come to the two-dimensional Cartesian coordinates. You easily can write or understand that the in two-dimensional Cartesian coordinate system, the uh, heat conduction equation is given by del u del t, that is equal to h square del u del x square plus del t u del y square. That is, in this case, both the coordinates x and y will be there, and obviously t is another function. Obviously u is another function of t. So in this case, u is a function of x, y, and t. So that is written here. Let u x y t is equal to x function of x, y function of y, and t function of t. Now just find out the value of del t, that is here, and del 2u del x square, that is here, and del 2u del y square, that is here. Okay. So now substitute these values in this equation, that is equation number 7. We can obtain that xy dt by dt, that is equal to yt d2xy dx square plus yt no, it will be xt, x into t. Okay, this will be x into t, then d2y by dx square, d2x by d2 d2 here, d2y by dx d2y by dx square, it will be capital X. Okay, it will be capital X. So now dividing this equation both sides of this equation by x, y, t and h square, then we have 1 by h square 1 by t dt by t, that is equal to 1 by x d2x by dx square plus 1 by y d2y by dy square. And you see that from this relation that this term is independent of x and y, and these two terms is independent of t. So all of these, and you can obviously further say that this term is independent of y and this term is independent of x. So all these terms, that is this term, and this term, all are constants. And say that constant is minus k square. And obviously here k is known as the separation constant. So from the given equation, or the two-dimensional heat conduction equation can now be separated into three ordinary differential equations, which are given here: 1 by h square t dt by dt, that is equal to minus k square, and the second one is from this term 1 by x d2x by dx square is equal to minus m square, say that is another constant, and this is written here 1 by y d2 y by d2x by d2y by dy square, that is equal to another constant. So these will be y. Sorry, it is written mistakenly. D2y by dy square, and all of these will be these will also be y square. So that will be constant. Now we have to find out this value of this constant. See here, this term is equal to this term and this term. So if this term is taken as minus m square, so this term plus this term should be this term, that means minus k square. And from this, that means minus k square is equal to minus m square plus this constant. So this constants will be minus this constants plus this constant if you change the slide. So from there you can easily understand that this constant will be minus k square plus m square, that is equal to minus of k square minus m square. So from the first equation, h square 1 by t 1 by h square 1 by t dt by dt minus k square, you can write dt by dt, that is equal to minus k square th, or dt by t is equal to minus h square k square dt. And if you integrate this, you can write ln t log t is equal to minus k square h square t minus k square h square t, and then log plus log a. Log a is another constant. So from here, log t by a is equal to h square k square t, and from there t function of t will be a e to the minus k square h square t. H square t, mistakenly here h is written, and here also mistakenly written h. So this h will be h square and this h will be h square. So a e to the minus k square h square t. And from the second one, that is 1 by x d2x by dx square is equal to m square. And from here, d2x by dx square plus m square is equal to 0, and this gives you a solution. That is, in this case, you have the solution x function of x is equal to a1 cos mx plus b1 sin mx. Okay, now from this one, 1 by y d2y by dy square, see here it will be dy square, that is equal to constant, that is we have calculated that that value is minus k square minus m square. And so from here d2y by dx square plus k square minus m square into y is equal to 0, and this give you a solution. Y is as a2 cos root over k square minus m square y plus b2 sin root over k square minus m square into y. So the complete solution is here. uh, uxyt is equal to a1 cos mx plus b1 sin mx, then a2 cos root over k square minus m square y plus b2 sin root over k square minus m square y, and into a e to the 1 k square a square t. This is equation number 2 and 8, and this is the complete solution. Now this relation is rewritten here once again. That is nothing different from this. That is, this relation is here written once again. This is equation number 8. Now let us use the following boundary condition. Let us suppose that you have given this boundary condition, that is u equal to 0 when x equal to 0 and x equal to a. That means u0 yt and ua yt, both of these are 0. This is boundary condition number 2. And u equal to 0 when y equal to 0 and y is equal to b. That means ux0t and uxbt is equal to 0. So there is no problem to understand these boundary conditions. So now we wish to use this boundary condition which is to be applied on this solution. Now just use the first boundary condition, the first part of the first boundary condition, that is x equal to 0 at x equal to 0, u equal to 0. So I first write u equal to 0 directly from here, since in this case u equal to 0. That would be from here, since x is 0, so a1 cos 0, that will give you 1. This term is 1, so a1 into 1. So that is 1, a1 into 1, and this term will be b1 into sine 0 will be 0, so b1 into 0. Okay, b1 into 0 into other terms. Here are the other terms. So that will be 0, so a1 from here will be 0. This will be b1. So a1 would be 0. So also for the second part of the first condition, that is x equal to a, u is also 0. So from here you can write the right hand side actually from here. Just see from here that you have already obtained that a1 here, that a1 is equal to 0. So this term will not be there, only this term will be there. So from this term b1 sin m into a, that is written here, that would be equal to 0 because all these terms are constant with respect to x. So that is equal to 0. So from here you can write that sin m is equal to 0, that means sin n. So from here m is equal to n pi by a, n is equal to 0, 1, 2, 3, etc. integer. So then equation 8 reduces to x, y, z, t, b first, because the term involved with the constant a1 is not here because a1 is equal to 0. So here will be b1 sin n pi x by a. It will be b1 sin n pi x by a, then a2 cos root over k square minus m square y plus b2 sin root over k square minus m square y, and then a e to the 1 k square h square into t. So this is the solution. See here it will be sin n pi x by a. So now using the boundary condition number 2, that means at y is equal to 0, and then from this equation, then in that case it is also 0. See here u equal to 0, then y equal to 0. So from this relation u equal to 0, that is equal to see from here a2 cos this term. So if y is equal to 0, this term will give you the value 1. So a2 into 1 is here, so, and this term will give you 0. So b2 into 0, and e to the power this term, a e to the this term is also there, and this term is also there. That would be 0. So from that a2 1 into b2 0, you can write it as 0. So from here a2 is 0. Now also from here, if also from here k square minus m square, you can write that is equal to that is equal to, you already obtained the value of m is equal to n pi by a. So since k square minus m square, we can write here the value of k square minus m square, that is equal to k square minus, here is the value of a this. So if substitute here, and this is equation, another equation. Now in this case we actually obtain this term will be there, and since a2 is equal to 0, so this term will not be in the solution. So the terms that will be in the solution are b1 sin n pi a into x, then b2 sin root over k square minus m square into y, and then a e to the minus k square is square t. These are the terms that will be in the solution. And also see here that boundary condition number 2, second part of boundary condition number 2, that at y is equal to b, u equal to 0. That gives you from this equation, because this term is not here, only this term, and this term, these three terms are there, will be there. So from this you can easily understand the value of b2 into sine root over k square minus m square into a is here, b is here, because you are replacing y by b in this case. That would be equal to 0, because it is equal to 0, and from here you can write sine k square minus m square into b is equal to 0, that is sine s pi. S is another integer whose value is 0, 1, 2, 3, etc. So from these two relation, from this relation you can also write k square minus m square is equal to s square pi square by b square. Okay, because this value is equal to s square. So this is another relation. This is equation number 10. This is equation number 11. See here that the left hand side are the same. If you compare these two equations, you can easily write that k square minus n square pi square by a square, that is equal to a square pi square by b square. Okay, this is it. So from here k square can be written as n square pi square by a square plus s square pi square by b square, that is equal to pi square into n square by a square plus s square by b square, and you write this as k n s square. First consider it. So now the solution becomes uxyt is equal to b1 sin n pi x by a, then b2 cos s pi y by b, and into a to the 1 as k square x square into t. So finally from here you write that b1, b2 and a, all these terms makes another constant, that is b, and sin n pi x by a sin s pi y by b into e to the power minus k square x square t. This is now the solution that comes. Okay. Now let us now taking all values of n and s, you will have x ux yt, that is equal to 0 to infinity, s equal to 0 to infinity, b n s sin n pi x by a sin n pi y by b e to the minus k square n s x square t. You already know that this is what is that is here. So to find the value of b and s, that is this constant, let us consider another boundary condition. Let us another boundary condition, that is u is equal to uxy, u0xy at t is equal to 0. When t is equal to 0, then u is equal to uxy. Consider this. This is the boundary condition. Then from equation number 3, you just write t is equal to 0 in this expression. So that will give you n equal to 0 to infinity, s equal to 0 to infinity, b n s sin n pi x by a sin s pi y by b into 1. This term will give you, this is the term that is related to t, that this will give you 1. So it is equal to u0xy. So now multiplying both sides of this equation, first this one, multiplying this u0xy by sin n pi x by a sin s pi y by b, and integrate these from 0 to a and 0 to b for x and y. Then you will have from this term 0 to a, 0 to b, u0xy, then you have, since you are multiplying by sin n pi x by a, then sin s pi y by b into dx dy. This is the integration of these upon multiplication of these two terms, and that will give you, so to multiply from this, what you can obtain, that is 0 to a, 0 to b, this bns is there, and this sin n pi x by a and this sin n pi x by a, that will give you sin square n pi x by a, and the next term will be sine square s pi y by b dx dy. So that is equal to dns. Now by 4 I am dividing it by 4, so here is 2, another a 2 is there. So 0 to a, just separate this integration. 0 to a 2 sine square n pi x by a dx, 0 to b 2 sine square s pi y by b dy, that is equal to this term. So this give you, so and this can be written as 1 minus cos 2 n by x by a, and this can be written as 1 minus cos 2 s n y by b. And you know that the differentiation integration of this will give you sine term, and this will also give you sine term, and if you use the limits 0 to a, 0 and a, that will give you 0. So the result from these two terms will give you null. So only result that will come from this expression are for 1 into dx and 1 into dy, that is integration of x and dx and integration of dy. That will give you b ns by 4 from here a, and from here b, that is 0 to a, 0 to b, u x 0 xy sin n pi x by a sin n s pi y by b dx dy. And from where bs ns is equal to 4 by ab, 0 to a, 0 to b, u0 xy sin n pi x by a sin s pi y by b dx dy. So therefore the complete solution is here. U x y z, that is equal to 0 to infinity, s equal to 0 to infinity, 4 by ab, 0 to a, 0 to b, u0 xy sin n pi x by a sin s pi y by b dx dy into sin n pi x by a sin s pi y by b into e to the minus k ns h square. This is the complete solution. Just use the value of dns in this expression in equation number 13. That means in this expression. So this is the complete solution of the heat conduction equation in two-dimensional cases. Now come to the third one, that is conduction equation, solution of conduction equation in two-dimensional polar coordinates. So you already know that in case of two-dimensional polar coordinates, the Laplacian operator is given by del 2 by del r square plus 1 by r del r plus 1 by r square del 2 by del theta square. So if you use this Laplacian operator for two-dimensional polar coordinates in two-dimensional heat conduction equation, that will lead as del u del t is equal to h square del u del r square plus 1 by r del u del r, then plus 1 by r square del u by del theta square. This is equation number 15. Now to solve this, the conventional or the method that you will employ is the method of separation of variables, and according to that method you can write u r theta t is equal to r function of r theta function of theta t function of t in this way. And here just find out the values of del u by del t, then del u by del r square, and after that del u del r and del u by del theta square. These values are computed here, and now to substitute these values in this expression. That is in equation number 15. So after doing that, we can get r theta dt by dt, that is h square, theta t d2r by dr square plus theta t by r dr by dr plus r t by r square d2 theta by d theta square. So equation number 15 is converted to this equation. Now dividing both sides of this equation by r theta t into h square, you can achieve this from this equation as 1 by h square. This equation can be then converted to 1 by h square into t dt by dt, that is 1 by r dt by dr square plus 1 by r dr by dr plus 1 by theta r square t2 theta by d theta square, that is equal to a constant. That should be constant because the left hand side is only a function of t, and the right hand side, first part of the right hand side is a function of r only, and this is the function of theta and r. Okay, so these actually all these terms are independent of t. So these is equal to these should be a constant, that is equal to minus lambda square say, and it is called the separation constant. So also you consider this value in case of these two terms in the right hand side. The first term is dependent on theta, and this term is dependent on both theta and r. Now if you consider that this term without these r square, that means 1 by theta d square theta by d theta square, that is here 1 by theta d square theta by d theta square. You say this is equal to n square, another constant. So then you can write from this expression that the right hand side, from the right hand side of this expression you can write this term is here 1 by r d2r by dr square plus 1 by r dr by dr. Then you already have taken here 1 by theta d2 by d theta square is n square minus n square. So this whole term will give you minus n square by r square. That is equal to minus lambda square. And from here, this these two terms is here, no problem is there. So then this lambda square is there and minus n square by r square, that is equal to 0. So from here you can rewrite this expression as d2r by dr square plus 1 by r dr by dr plus lambda square minus n square by r square into r is equal to 0. Okay, you can write this from this equation, and you know this expression, that is expression number 18 or equation number 18, is the very well known or the celebrated Bessel's equation, and this Bessel's equation having the solution uh, like this. R function of the solution for R will be a jn lambda r plus b yn lambda r, where a and b are obviously two arbitrary constants, and jn is the Bessel's function of first order for the first kind. So Bessel's function of first kind for the order n, and yn is the Bessel's function of second kind for the order n. So this is the solution for R. And now from equation number 17, that was written here that 1 by theta d2 theta by d theta square equal to minus n square. From here you can write d2 theta by d theta square plus n square theta is equal to 0, and which has a solution theta function of theta is equal to c e to the power plus I n theta, and you can also write it as c1 cos n theta plus c2 sin n theta. This is equation number 20. And now come to the left hand side of this expression, that 1 by h square t dt by dt, that is equal to minus lambda square, that is here, and from here dt by t is equal to h square lambda square dt, and from here if you integrate this, log t is equal to minus h square lambda square t plus log a1, this log a1 is the constant, and from here you finally get t function of t is equal to a e to the power minus h square lambda square t. So therefore the complete solution is, this part is for R, so a jn lambda plus b yn lambda, then this term c1 cos n theta plus c2 n theta, and finally this term a1, say it is a1 e to the minus h square lambda square t. This is equation number 20. Now in case of when r tends to 0, then you know that yn lambda r, it tends to infinity, and then b should be 0, and then you can write from this expression that u r theta t is equal to b jn lambda r into the minus h square lambda square t c1 cos n theta plus c2 sin n theta. Here we have substituted b is equal to a1a. That should also be a constant. And from here you can also write b jn lambda r e to the minus h square lambda square t into c e to the power plus minus I n theta, because we can write this as plus minus I n theta. Now from here, because in this case you can write this as, and then from here you can finally write u r theta t is equal to a jn lambda e to the power minus a square lambda square t plus minus I n theta. This is equation number 21. So now considering all values of n, the complete solution now takes the form u r theta t is equal to n is equal to 0 to infinity a n jn lambda e to the minus k square lambda square t plus minus I n theta. So this is the complete solution of heat conduction equation, two-dimensional heat conduction equation for the polar coordinates. Okay, this is the complete solution. So we have actually solved the heat conduction equation up to two-dimensional polar coordinates. So left thing is to solve this equation in three-dimensional Cartesian, then cylindrical, and finally spherical polar coordinates, and that can be done done by following the exact methods that was used to solve the wave equation in case of three-dimensional Cartesian cylindrical polar coordinates. Just use the same process, and this is your homework. Now this is the end of the solution of three important partial differential equations. That is number 1 is Laplace's equation, number 2 is wave equation, and number 3 is heat conduction equation. Now we will enter to the to solve some problems. Here first problem is solve the following differential equation del u del x, that is equal to 4 del u del y. You have given a um, boundary conditions, that is a condition that is u0y is equal to 8 e to the minus 3y. So rewriting the given equation here is that, and you can solve this by taking uxy is equal to uxx yt, and then find out the value of del u del y, that is here, and del u del x, that is here, and then from this expression you can write 1 y dx by dx, that is equal to 4x dy by dy. Now so dividing both sides by xy, that is 1 by x dx by x, that is equal to 4 by y dy by dy. And the left hand side is the function of only y and x, and the right hand side is the function of only y. So this is independent of y and this is independent of x. So both of them are constants, and that is taken as k. That is called the separation constant. So we obtain here two ordinary differential equations from this partial equation, and that are given here 1 by x dx by x, that is equal to k. And after that is clear, and the solution of this, here is the complete solution is given here, that would lead you to x is equal to a to the kx. And another solution is another ordinary differential equation is 4 by y dy by dy, that is equal to k. And this is the method process of its solution, and finally you get y is equal to b e to the k by 4y. This is another solution. So you will consider these two solutions. The complete solution becomes uxy is equal to a to the kx, b to the ky by 4. Both of a and b are constants, arbitrary constants. And from here you can write c e to the k x plus y by 4, where c is equal to ab. Now the boundary condition is u0y, that means that x equal to 0, u is equal to a 8 e to the minus 3y. Now from this equation you can write ux is 0 here, since it is 0 here, so u0y, that is equal to c e to the power, here x is 0, so c e to the ky by 4. Now compare this relation with this relation. You can easily understand that c is equal to 8, since there is 8, and then here is ky by 4, that is equal to minus 3y, and from here k is equal to minus 4. Now just write these values of c and k in this expression, that will give you uxy is equal to 8 to the minus 12 x plus y by 4, and this is the simplification, and finally you get e to the power 8 e to the minus 3 into 4x plus 1. Now another problem is here. You have to check the nature of this, or the type of these equations. Here is the equation. Here are the equation 1, 2, and 3. There are 3 equations, and to find out which kind of equation are there, you have to write the just general expression for a partial differential equation, that is written here: a d2 u by dx square plus 2h d2y by dx dy, and this, that is equal to 0. Just compare this equation to this equation. You can easily find out, you can readily find that a is equal to 1, h is equal to 0, b is equal to 1, f, g, c is equal to 0. And from here ab minus h square is greater than 1, that is greater than 1, so it is elliptic. Now for the second equation, you will find that ab minus h square is equal to minus k square, so that should be less than 0, so it is hyperbolic. And in this case, for the third problem, you can show that ab minus h square is equal to 0, so it is parabolic. So here is the explanations are there, so you will just go through this. Now another problem is here: solve the equation del u del x is equal to 2 del u del t plus u under the condition ux0 is equal to 6 e to the minus 3x. This is the condition, and you have to solve this problem. Now write that equation here once again: del u del x is equal to 2 del u del t plus u. And here to solve this equation, you know that you have to write uxt is equal to xxt. Obviously in the case of separation of variable method. And now calculate here, from here del u del x, that is here, and del u del t, that is this. Now substitute this in the mother equation, that is in this partial differential equation, that will give you 1 by x dx by dx, that is equal to 2 into 1 by t dt by dt plus y. And you will get it after. First you have to substitute these values and these values there, and then dividing both sides by xt. That will give you this. Okay, xt, because here u is nothing but xt, so if you divide it by xt, that will give you this one. So therefore this term is independent of y, and this t, and this term is also independent of x. So these and these both are constants. So that is from here, so you can write 1 by x dx, that is equal to k. That k is the separation constant, and from here you can easily find out the value of log x. You can find out the value of x. This is the process of solving this. So that will give you x is equal to a to the power kx. And also another one is 2 by t dt by dt plus 1 is equal to k, and from here you can write dt by t is equal to half k minus 1 into dt from this relation. And after solving this, you can get this is the complete methodology and the complete steps, and there is no problem to understand it. And finally you get t is equal to b e to the power half k minus 1 into t. So the complete solution is here, uxt is equal to a e to the power kx into b e to the power half k minus 1 into t. Here a and b gives you another constant c, e to the power kx plus half k minus 1 into t. This is equation number 2. Now we have to apply the boundary condition that was given, that is here ux0 is equal to 6 e to the minus 3x. Now using t is equal to 0 in this expression, you have ux and 0, that is equal to c is here, e to the power kx. This term will not be there, e to the power kx. Now comparing this equation and this equation, you understand that c is equal to 6 here, and another one is kx is equal to minus 3x, and k is equal to minus 3 from here. So now writing this value of c and k in the solution, general solution of u, that is here ux is equal to 6, c is replaced by 6, e to the minus 3x plus half into minus 1 into t, that will give you 6 e to the minus 3x minus 2t. So the solution is this. This is the complete solution. Now another problem is here, solve d2z xy del x del y is equal to x square y, subject to the condition z x0, that is equal to x square, and z1 y is equal to cos y. So here is the given equation, del 2z xy del x del y, that is equal to x square y, and from here you can write this, the left hand side as del x or del z by del y. It is no problem is there, and that is equal to x square y. And now from here, if you integrate this expression, you will get in the left hand side z del z by del y, that is here, and you can integrate this expression in two ways. Number one is with respect to x, number two is with respect to y. First case, if you integrate this with respect to x, then in that case y is constant. So del z by del y would be from here x cubed by 3 into y plus c1, that is a constant, integrating constant, but since in this case y is taken as constant, so this constant c1 should be a function of y, that is written here. So similarly, if you integrate and from here, so from this is okay, this is here, and similarly if you integrate this expression further with respect to y, that will lead in z is equal to x cube y square by 6, y integration of y is equal to y square by 6, plus in this case, so a function will be there, that is phi y, because integration of this term will give you another function of y that is given as, that is taken as c1y, sorry, phi into y, because integration c1 y dy, c1 dy, c1 function of y, it should be function of dy, that is equal to phi, that is phi y, and in that case x was taken as constant, so the another constant will be c2 into x, c2 function of x. So this is equation number 1. So now just from the boundary condition, first boundary condition, that is zx0, that is equal to x square. So zx0, that is equal to x square. From this relation you can write x square, since the value of z is in this case x square, is equal to, in the here x is 0, so that will give you 0, then phi of 0, because in this case, sorry, because in this case y is 0, so since y is 0, so first term will give you 0, and then this term will give you phi 0, and here is c2x, and from here c2x is equal to x square minus phi 0. So z is it can be written from equation number 1 as x cubed y square by 6 plus 5y plus here is the value of c2. So x square minus 50. So now another condition, that is z 1y. So in this case x is taken as 1 is equal to cos y. We can write here that from this relation cos y is equal to this from here y square by 6 then plus 5y then plus 1 minus 50, and from here 5y is equal to cos y minus y square by 6 minus 1 plus 50, and so the complete solution is z xy is equal to y square by 6 x2 y square by 6 minus y square by 6 plus cos y minus 1 plus 50, and y square by 6 is the common term from these two terms, so this is done here y square by 6 x2 minus 1 plus cos y minus 1 plus 50. This is the complete solution of the given differential partial differential equation, that is this. Now come to another problem. You have to solve the equation del 2u del t square is equal to c square del 2u del x square, where c square is a constant, and you should be used the separation of variable method, and you have given boundary conditions u 0t is equal to 0 and u lt is equal to 0 for our value of t. So now here is the given equation del 2u del t square is equal to c square del 2u by del x square, and we are very familiar to solve this type of equation, and you know the process and there is the steps, and no, there will be no problem to understand these processes. And so from this expression actually we get two ordinary differential equation. One is 1 square square t 2t by dt square, and another is 1 by x d2x dx square, and both of them are constant, that is taken as omega square. So from first relation you can write this, and from here d2t by dt square omega square c square t, that is equal to 0, and this will give you a solution for t as a cos omega ct plus b sin omega ct. Every all are constants. And another equation is 1 by x d2x dx square minus omega square, that will give you a solution of 3 cos omega x plus d sin omega x. So the complete solution is here u x t is equal to a cos omega ct plus d sin omega t, 3 cos omega x plus d sin omega x. This is equation number 2. Now we are here to use the boundary conditions. From the boundary condition number 1, that is u 0t is equal to 0, we can write from equation number 2 that u 0t is equal to 0, so left hand side this is equal to 0, and then a cos omega t b sin omega t is a constant, since only x is has the value 0. So from this term c, this first term will give you c into 1, and this term will give you d into 0. So from here you can write c is equal to 0. So now the solution takes the form uxt is equal to this term, and from here d term d sin theta will be, this sin omega x will be there. So d sin omega x and this term is there. Okay, this is equation number 3. Now another boundary condition that is given ult that is equal to 0, that is for the value of x at L. So that is also 0. So that is, so left hand side is there. From we can obtain from this expression, that is from equation number 3, that left hand side is 0, that is equal to d sin omega, and here x is L and all these terms, and the right and the second term is here, that is equal to 0, and from here sin omega L is equal to 0, that is equal to sin n pi in 0 1 2 etc., and from here you can calculate omega as n by L. So just write the value of omega in this expression, that will give you uxt, that is equal to sin d sin n pi x by L, then a cos omega ct by n pi ct by L plus b sin n pi ct by L. Just substitute here the value of omega in this expression, that will give you this, and finally from here you can write sin n pi x by L, a1 cos n pi ct by L plus a2 sin n pi ct by L, where a1 is ad and a2 is a2d. So no, a2 is equal to b into d, not b into d. So another boundary condition that can be given here is t is equal to 0. If you have, suppose that you have given another boundary condition, that is at t is equal to 0, ux0, that is equal to fx, and del u del t at t is equal to 0, that is equal to gx. So let us now use this boundary condition. Now from this equation at t equal to 0, so then u becomes fx. So left hand side is here fx, that is equal to sin n pi x by L, and since in this case, see here, t since t is equal to 0, so this term will give you a1 into 1, that is here a1, and this term will give you a2 into 0. So you can write from here fx is equal to sin n pi x by L into a1, and from here a1 is equal to fx by sin n pi x by L. And now del u del t, just differentiate this expression, differentiate this expression, that will give you sin n pi x by L, okay, is there, and differentiation of this will give you minus cos n pi ct by L into n pi by L with a1 constant, that is there a1 sin n pi by n pi c by L, then sin n pi ct by L, okay, plus no, this term will be only n pi c by L, sin is not here, so a1 into n pi c by L, then sin n pi ct by L plus n pi c by L into a2 into sin theta sin n pi ct by L will give you cos n pi ct by L. So at t is equal to 0, sin n pi x by L, this term will give you a1, this term will give you a1 into, due to this term 0, plus n pi c by L a2 into 1, that is gx given. So from here a2 is equal to gx by n pi c by L sin n pi x by L. So the solution then becomes ux is equal to sin n pi x by L fx cos n pi ct by L plus by sin n pi x by L plus and then plus gx sin n pi ct by L by n pi c sin n pi x by L. Just substitute the values, you can obtain this. So this is the final solution. So this is the final solution. Okay. Now assuming another problem, that is assuming separation of u r theta in this way, and show that the Laplace equation can be decomposed into three different equations. So Laplace equation can be decomposed into three different equations. You have to solve, you have to prove it first, and then there is a condition, that is in the phi equation, phi of theta, phi plus 2 by that is equal to phi of phi. You have to use this condition. So now here you know that the Laplacian operator for three-dimensional spherical polar coordinate is given by del 2 del r square plus 2 by r del r plus 1 by r square del 2 del theta square plus cot theta by r square del theta plus 1 by r square sin square theta del 2 by del phi square. So now if you use these for the function u, that means that will give you Laplace equation in three-dimensional in spherical polar coordinate, that will give you equation number 1, and that is and the solution would be this equal to this. Now from equation 1, just you substitute the value of del 2 u by del r square, del u del r, and all the partial derivatives, the value of all the partial derivatives, that will lead you this theta phi d2r by dr square plus 2 pi r theta phi dr by dr plus 1 by r square r phi d2 theta by d theta square plus cos theta by r phi d theta by dt, that plus r theta r square sin square theta d2 phi by d phi square, that is equal to 0. Now just divide both sides by r theta phi, that will give you this expression, okay, that is equal to 0. And from here just write this last term to the right hand side. So these are all these terms except the last term is here, and that is equal to minus 1 by r square sin square theta 1 by phi d2 phi by d phi square. Now just multiply this equation, multiplying this equation on both sides of this equation by r square sin square theta, then that will give you 1 by r square d2r by r square plus 2r dr by dr sin square theta, that is equal to, that would be plus sin square by theta d theta square by d theta square plus cos theta d theta by dt. So from these two terms you will have this, and that is equal to minus 1 by phi d2 phi by d phi square. This is equation number 2. So the right hand side is only the function of phi, and it is independent of r theta. Hence both of the right hand side and left hand side are constants. So these and these will be constants. So from here, so you can write minus 1. You can write 1 by phi d2 phi by d phi square, that is equal to minus m square. So it is a constant, and this is the phi equation, and I write it as equation number 3. Then from equation number 2, that is from equation number 2, you can write 1 by r square d2r by dr square plus 2r dr by dr plus 1 by theta d2 theta by d theta square plus cos theta d theta by dt into sin square theta. Here this sin square theta are taken common term, that is equal to minus 1 by phi d2 phi by d phi square, that is equal to m square plus m square. So from here you can write these, all these terms is here, and this sin square theta is divided these m square. So and that has been taken in the left hand side. So m square by sin square theta, this term, and m square by sin square theta, that is equal to 0. Or from here 1 by r square d2r by dr square plus 2r dr by dr, that is equal to, just take this term to the right hand side, these two terms. So that is 1 by theta d2 theta by d theta square plus cos theta d theta by dt plus m square by sin square theta. So here also the right hand side is a function of theta alone, and the left hand side is the function of r alone. So both of them are also constants, and this constant is taken as n into n plus 1. So this value is taken as n into n plus 1, and then from this equation you can write you can write that these value is equal to n into n plus 1, because this term and this term both are constants. So that is written here. So from this relation d2 theta by d theta square plus cos theta d theta by dt plus n into n plus 1 minus m square by sin square theta into theta is equal to 0. From this relation you can write this. This is equation number 6. Thus Laplace equation is now decomposed into three separate equations. Number one is this. This is one kind of equation that is dependent on phi, and then the second one is here. The second one is this is dependent on r only, and the third one is this, that is dependent on theta only. So here we succeed to separate the Laplace equation in spherical polar coordinates into three different differential equations that are given in equation 5 is here, or 3 is here, given in 3, 5 and 6. Okay. Now this the first problem. The first problem has been solved. Now the second one is, the phi equation is given by equation 3. Just look at equation number 6, equation number 3, that is here. So that is once again written here. So 1 by pi d2 pi by d phi square is equal to minus m square. That will give you this, and that has a solution a to the plus minus I m phi. That can also be written as a cos n phi plus b sin n phi. All of a b, so all are every constant. So no problem is to write these as in this fashion. So the condition is phi plus 2 pi is equal to phi of phi, and that will give you from this expression that phi of phi plus 2 pi is equal to phi of phi, that is equal to a cos m into phi plus 2 pi plus b sin m into phi plus 2 pi. So that will basically give you the same result, that is a cos n pi plus b sin n pi. So this is here phi of phi is equal to a sin a cos n pi plus b sin n pi. This is the solution. So here is the end of this lecture, end of this class, and you need to rectify the error that was in different slides. While you will study, you will just correct those errors, and then this class will be complete. And so we will see in our next class. So I am ending this class here.